Yeah, it's like that. I think people get colds and all kinds of things, and then there's all the Black Friday shopping. And, yeah, so it's dark, so you want to stay in bed, and you don't really want to go anywhere, and the weather's nasty. Yep. I can understand it, and moreover, they can watch it at home. To walk up and give me. Okay, let's get started then. The plan for today is to first check the homework and then do something else, which is very specific. Anybody have anything to check? If you have, then check. If you don't have, if you got a different solution to mine, shout. I think this is correct. And it's the same exercise I gave the students last year, and nobody complained. So presumably that's correct, but it's possible that there's always an error everywhere, right? I mean, no matter how hard you try. Okay, so don't copy that. I'll put it on Moodle. And now you can mark your mark, if any. Do you remember the weak duality theorem? That's why I've got this reminder. Do you remember now? Okay, what it says is you've got the two LPs that are the dual of each other, and if you find a feasible solution to the maximization one and the feasible solution to the minimization one, then the maximization one is always the objective value is always at most as much as the objective value of the minimization problem among the two duals. Okay, and that's why one can be used as an upper bound for the other, and the other can be used as a lower bound for the one. Now, what we've been somehow what I promised you, and what I haven't delivered yet, is the fact that when you actually find the optimal solutions, if they exist, then the objective will be the same. Okay, so the situation is if you find any feasible solution to the one and any feasible solution to the other, you know which is larger and which is smaller. But if you find the optimal one, then the objective is supposed to be the same, as I promised. And so this is what we're going to prove today, and that's called the strong duality theorem. And that will then be it for linear programming. Okay, so linear programming is finished. And so when you look at your the second sheet in your handout, you'll see a huge homework, which is the plan for the remaining 2 weeks, because students love revision. So these are revision exercises about post-optimality analysis, and you'll do them at home, of course. How could I believe you're going to do them at home? Of course you're going to do them at home, and we'll go through all the problems in the remaining 2 weeks, and if there are no problems and everything is great and everybody solved everything, then you can go home and do your business. So the plan is clear. Now, okay, so now we've got the weak duality theorem as the starting point, and we want the strong duality theorem. But before we get the strong duality theorem, I said an important thing, didn't I? And I said
if the optimal solution exists. But does the optimal solution or an optimal solution always exist? No. When does it not exist? Remember? In the first year, we had two different cases, and there were two different cases, one completely different, even though they're not as completely different as you know.
Okay, so when you have a negative right-hand side.
When you have a negative right-hand side, then, well, you've been doing the second assignment, the third assignment.
Really,
right? You started with a negative right-hand side, and still you found an optimal solution. So having a negative right-hand side is not necessarily preventing an optimal solution. So there were two cases. One of them was a linear program it's called infeasible. And this was, as you certainly recall, if it has no feasible solution. Okay? So sometimes the constraints just exclude all possibilities for a feasible solution to exist, and then of course there can't be an optimal solution because there is no point that would satisfy all the constraints. Okay? And the second situation, yeah, unbounded. Yes, exactly. So a linear program is unbounded. What does that mean? What's the definition? Yeah. If the objective function can be made, well, not as, but I'll put arbitrarily large or small for minimization problems. Okay, so if you can find optimal solutions that make the objective function as large as you want, no matter what number you say, you can always find larger objective in a feasible solution, then it's unbounded for a maximization problem, and for a minimization problem, it's the converse. So you want to find a smaller objective value solution. Okay. Now we have these two cases when there is no feasible solution, and I said that the strong duality theorem promises you that if there is an optimal solution for, well, I don't know what I said. Well, so what did that promise? Said that if both have an optimal solution, then the objective value is the same. But in fact, it says more. It says that if one of them has an optimal solution, then also the other has an optimal solution and the objective value is. But it says even more than that. It says that you can't have, for example, you can't have I don't know what you can't have. Well, you can't have any kind of combination of feasibility and boundedness, or infeasibility and unboundedness between the two. So it's written here. Okay. Three statements. If one of them is unbounded, then the other is infeasible. both ways. And if one of them is feasible and bounded, and they're both feasible and bounded, and have an optimal solution, and the objective is the same. So in the remaining 35 minutes, we'll prove this, and then we'll happily move on to the revision. Any questions so far? No. So let's. Okay. So one is easy. How do you prove point number one? Okay, so this is proof. Because you can easily prove the contrapositive. What's the contrapositive? Contrapositive is if D is not infeasible, in other words, if D is feasible, then P is not unbounded. So I'll write P is bounded. Okay, in logic, this is equivalent to what one says. Is this true? Why? Goes directly from here. So if D is feasible, then you find some feasible Y. You have an upper bound, and so P can't have arbitrarily large objective values because it's bounded. Make sense? Oh dear. This follows directly. From the weak duality theorem. D is feasible, it has a feasible solution that provides an upper bound, so you can't have arbitrarily large objective in the primal. Two is the dual of that statement, so so this follows just as directly from the weak duality theorem. Okay? Except here you're saying that if E is feasible, then this can't be arbitrarily low because the Cx got a feasible solution. But plug the feasible solution for X and you get the low bound. Okay? So now it's time to draw a table. I have to concentrate. So P can be infeasible or unbounded or feasible and bounded. And D could be infeasible or unbounded or feasible and bounded. Okay. In theory. Now, if P is unbounded, so if we're here, then by one, which we just proved, D is infeasible. So if we're here, unbounded, in this row, we can't get into those. So this doesn't happen. And similarly, if D is unbounded, then P is infeasible, so we can't be here. Okay, so this is possible. Where's green? One of them being infeasible, that can happen. And therefore also this can happen. It's also possible that they're both infeasible. Nothing in the theorem contradicts them both being infeasible, so that can happen. As an exercise, you can devise an LP which is both infeasible in the primal and the dual. Now, what we're saying is, now this view, that if one of them, say primal, is feasible and bounded, then we're claiming that it's not here, that it's there. Okay? So the third part is telling you if P or G, either one of them, is feasible and bounded, then they're both feasible and bounded, so this can't happen. And moreover, the objective value is the same. So, so what we need to prove still is that this can't happen. Okay? But okay, but also one should say that because they're kind of, it's sort of symmetric. So if P is feasible and bounded and we prove that D is feasible and bounded, then we don't have to do anything anymore, because if we had started with D, then the same proof essentially gives us that D is feasible and bounded because they're the dual of each other. So it doesn't matter which side we start on. Okay. So the only thing we need to prove is that if P is feasible and bounded, then all these nice good things happen that that point number 3 promises. Okay, so well, the proof that I'm telling you relies on the simplex method working. Okay, so we trust the simplex method. And we know that it will find a basic feasible solution which is optimal. Okay. So An optimal tableau will look like this. What's it going to look like? There's some basis. There's the objective. There's some val. There's some x's, and there's some s's. What is there? Aisha's looking for it. What is there? Like this. So this is what it's found. What is there? This is capital B, just in the right top. So take the MB matrix, its inverse. That's what's here. But we don't really need it now. And the linear combination of the rows of this matrix given by the objective coefficients of the basic variables, this thing here, and the linear combination of the columns of this matrix given by the right hand side of the constraints is here. Okay. So that we know. And we also know that it's optimal. So what does that mean? How can you tell that when you get a tableau that it's optimal? Pardon?
No negatives in the values or individual.
Exactly. No negative number, no negative entries either here or anywhere there. Because we're talking about P, it's a maximization problem, which is somewhere on the sheet which you have in front of you. So there won't be any negative entries here, and there won't be any negative entries here. So that means, among others, this is greater than or equal to 0, and CB and B inverse. This is greater than or equal to 0. But also, we know that if we put x star to be this vector MB inverse B, we know that x star is feasible for the primal, right? So we multiply A MB inverse B, that's going to be greater than or equal to 0. So it's kind of easy to lose track of what is what, but you know that MB inverse, that's this matrix, and it's M by N, so it's a square matrix. Well, course it's squared because we're taking an inverse. Better be square. And this is a column vector, okay, of all the x's. What am I doing? Not true, is it? No. Well, that's something that I didn't want to say at front. We shouldn't put this. So just the basic variables in x. Okay. Because of course the MB that's not giving us the x's, it's giving us the values of the basic variables rather than decision variables. So that's all rubbish complete. So this should be x star. Oh, I've got the correct. Which I only got because of Miriam always complaining last year. My writing wasn't tidy enough. So yeah, so a times x star, but I don't think we need this. What we do need, however, is something we don't know. So put y star equal to CB MB inverse, but transpose. Well, the transposition doesn't do much. I just want a column vector, and what I'm getting is a row vector. So I transpose it to get a column vector because I want an optimal solution of the dual, or any solution of the dual, to be a column. All right, that's how it's written. Yeah, so now, what is that good for? Why did I call it y? Very suggestive, isn't it? It's also something I've been promising you. So I called it y because I want to show that this is a feasible solution of D. Okay. So how do you show that it's a feasible solution of D? Well, first you have to show that it's well, first. One of the things is that it's non-negative. Well, it's non-negative because that's the criterion. So that's okay. Y star is non-negative because tableau is optimal. Tableau is optimal. Now I have to concentrate. Where are we? Ha. Now, in fact, we need to. So, okay, we'll get that. So, is ATY star or negative? That's oh no, not negative. Concentrate. Jan, concentrate. You're messing up. Is this greater than or equal to C transpose? That's that's the constraints of the dual. Well, yes, if and only if y star transposed times A is greater than or equal to C. Oh, that doesn't solve anything, does it? We've just transposed both sides. But this is true if and only if what's y star now? Y star is CB MB inverse transposed. So y star transposed is CB MB inverse. CB MB inverse times A is greater than or equal to C. Is this true though? This is true if and only if this minus C is greater than or equal to 0. Is that true? Why?
What you
That is exactly what you have up there. So I lied to you when I said we will need it. So this is there. So being optimal means that this is greater than or equal to 0, and CB MB inverse A minus C is greater than or equal to 0. I fixed it there, so nobody can tell from here that I forgot to. A good day for me. Hope that's not a good video. Okay, so back to this. Feasible. Well, y star being feasible for the dual means that it's non-negative, which it is because the tableau is optimal. And this being true, but this is equivalent to that being non-negative. That is non-negative because of optimality. So if we find an optimal solution to the primal, then we found a feasible solution to the dual sitting down. Okay. In fact, that's very illustrative. It's very enlightening. Because I've always been talking about optimal, but being optimal is actually the same thing as being dual feasible. Okay? So you can always find, when you have a tableau, you always have some kind of primal solution in the valve, basically, whether it's feasible or not, but you have a solution corresponding to the space. You also have a solution of the dual, whether it's feasible or not. It's feasible exactly when this is all negative, and this is all negative. So being optimal, having finished solving to optimality, is the same as the dual being feasible, and of course vice versa, being feasible in the primal is the same thing as the dual being. Okay. But that's just one part of what I was framing, and that's this part. Right? So we now know that this, the primal is feasible and bounded, and we found an optimal solution, then the dual can't be infeasible, we've just found a feasible solution. This can't happen, and this can't happen by a symmetric argument. Primal and duals really doesn't really matter which, the dual of each other. So now we know that it can, well, this we know quite well, that this is possible. But the remaining claim of the strong duality theorem is that now the objective values are the same. So that's the only thing that still has to be checked, is that the objective functions have the same value. I'm going to there. Got this. But now I have to concentrate, because the question is, so we've had this point which asks whether it's feasible, and is this feasible. So I should put it here to make it clear. So my star is a feasible solution of the dual. Now, the last thing that we want to show is that Y star is also optimal. So is Y star an optimal solution of the dual as well? And okay, so what is the objective value of this? So the objective of the dual for this Y star is well, it was to minimize B transpose Y. So it's B transposed times Y star. Okay. But remind me again, what is Y star? CB MB minus 1 transposed. Okay, well, this is just a number. And it's not a vector, it's not a matrix. Just actually the inner product or scalar product, or what we call it, each of the vectors. It's just a number. Trust me. It is just a number because it's the objective value. That's the beginning. So when it's a number, we can transpose it and it's equal to itself, because if you just have one number, you can transpose it any way you want. Not a vector. Okay, so this is equal to its transpose, which is CB MB inverse B. Because transposition swaps the order of multiplication, as you probably know from linear algebra. I hope you do. And what's this? So MB inverse B, that is the thing I messed up with the X star. Right? That's the basic, these are the values of the basic variables. So this is Cx star. C. Yeah. This is the objective. This is my X star. It's a feasible solution of the primal. Okay. So now this proves that. Well, it doesn't prove anything yet, does it? But what it proves is that we found a feasible solution X star of the primal and a feasible solution Y star of the dual with the objectives. So Vt y star, that's one of the objectives, is equal to the objective of the primal. And that's what we found. Just by looking at the tableau. Now, why does this have to be optimal for both? So x star for B and y star for B, why do they have to be optimal? No. It's because of this. All right. Did you mean 1 and 2?
Yeah.
Okay. So I don't know. I didn't understand. Yeah, but it's if you meant this, then you were right. Yes, because of this. So how could this possibly be larger? We're trying to maximize this. It can't be larger than this because y star is a feasible solution, so this gives us an upper bound. So if we reach that upper bound, we can't do any better. That must be the maximum. And similarly, how could this be smaller? Well, it can't be smaller because we found the lower bound by exhibiting feasible solution of the primal, so it can't get any lower, and so when it gets as low as it can, and it must be optimal. So this weak duality theorem implies that they're both optimal. So by the weak duality theorem, both x star and y star are optimal, and that I think is everything that we were promised by the strong duality theorem. That's it. That's it for questions. I don't think I have. So as a byproduct of this proof, what we get that the thing that I kept promising you, that when you stop moving things around again. Things that I promised you before, namely that you don't have to solve both the primal and the dual, because when you've solved one of them, the optimal solution to the other one will be down there. You trusted me. You never questioned me, which is not good. You always question what I say. But now I've actually proved that it's the case. So now you can trust me that once you've solved one of the problems of optimality in the simplex method, then this bit of the tableau gives you the true optimal solution. That's it. Any questions? So you know what to do for next time. Go through the problems, try to solve, well, at least the first 5 or so. Okay. So then we can go quite fast through the solutions in the and yeah. Okay, then I'll see you on Thursday.